Okay. So, the last section in Chapter 5, we're going to look at polynomial and rational inequalities, and the ways we would solve these inequalities. Now, you already know how to solve polynomial inequalities. You know, you're already familiar with that. Okay. When you're solving polynomial inequalities, you factor the polynomial. You treat it as equal to 0. Set each factor equal to 0, pick test values, get the intervals, and go on from there. And solving rational inequalities is essentially the same thing. It's the same process, but there is one exception. There's an additional exception. And that exception is, since it's a rational inequality, rational by definition is fraction, we have to consider where the rational term can be undefined, right? So basically there's another case where we're going to have a break point occur when we're dealing with a rational inequality. So when we're solving polynomial and rational inequalities, here's the process that we're going to do. You want to make sure, it's just to make sure the right-hand side of the inequality is 0. That's what we want to do. So if you have greater than, or if you have greater than or equal to 0, or less than or equal to 0, regardless of the inequality you have, you want the right-hand side to be 0. You want to factor the function completely. All right, so you want to factor the whole function completely, regardless if it's polynomial or rational. So let me make two lists here. F of x is a polynomial. F of x is rational. So in both cases you want to factor them. Just in case 2, you're going to factor the top and bottom. You're going to factor the top and bottom. And then you're going to make sure that the right-hand side is 0. Now, in the case of a polynomial, which you kind of already know how to do, you just factor it, set each factor equal to 0, and go from there. From there, it's the way you were taught earlier. Polynomial inequalities, we've kind of done them a lot already. The new topic so far is factoring, doing a rational inequality. So the big thing you want to do here is when you're doing a rational inequality, not only are you going to want to factor it, but you want to make sure there's only one fraction. There is only one rational term. That's important, and you'll see what I mean when we do them. But once you do that, basically you're going to just proceed normally. And you'll see what I mean when I do some examples. So the polynomial here, x cubed plus 2x squared minus 3x is greater than 0, clearly define the solution set. Okay. So you want to factor, this is a polynomial, so you want to factor it. So how would you factor this? Well, you could take out a GCF of x and get x squared plus 2x minus 3. And that's greater than 0. All right. Now what I'm going to do next is factor, this is a quadratic, so I want to factor that. Right? So if I factor that, I'm going to have x and x. The factors of 3 to give me 2, well, there's only 1 and 3. And then that has to be positive, and this is negative. Positive 3, negative 1. So now that this is completely factored, now what I'm going to do is I'm going to treat as x times x minus 1 times x plus 3 equals 0. I'm going to treat it like that because I want to find the breakpoints. Remember we did that? I want to find the breakpoints. We did the same thing when we did quadratic inequalities. So when I solve this equation, since it's factored, you know that you could just set each factor equal to 0. So this means x equals 0, x minus 1 equals 0, x plus 3 equals 0. This one's already solved for. Add 1 here, you're going to get x equals 1. And subtract 3 here, you're going to get x equals negative 3. So these are the breakpoints. Now remember, breakpoints are where your polynomial or your function could potentially change sign. Right? We talked about that in chapter 4. So to find the solution set, we need to create a number line. All right. And on this number line, we're going to include the breakpoints. So I'm going to put them in order. So negative 3, 0, and 1. So these are my breakpoints on my number line. Now, these 3 breakpoints give me 4 intervals. 1, 2, 3, and 4. So I have 4 intervals to check to see if this polynomial is positive or negative. So I'm going to do a test value for each one of these 4 intervals. I'm going to use my calculator for that. It's very similar to using the quadratic inequalities. Okay. So pick a value that's less than negative 3. I'll pick x is negative 4. There's nothing wrong with that. You could pick negative 10. You could pick negative 100. That's up to you. Doesn't matter. So let me get rid of that. So negative 4 stored in x. Let me type in the original polynomial, which is x to the 3rd plus 2x squared minus 3x. And that gives me a negative number, right? So negative 20, and obviously that's negative. So that means this interval is negative. All right? That's all it means. That means this polynomial is negative on this interval, which is from negative infinity to negative 3. Okay. Now pick a value on this interval from negative 3 to 0. So this right here was for this interval. And this right here is going to be for, I don't know, negative 1 is fine. So when you do that, negative 1 store in x, second enter, and I hit enter on that one, I get 4. Okay. 4 is positive. That means this interval is positive. I just do the same process for each interval. Pick a value between 0 and 1. A half works fine. You could also pick a quarter or 3/4. So 0.5, store that in x. Second enter, and I hit enter on that, I get negative 0.875. I don't care about the value, I just care that it's negative. So that means this interval is negative. All right, now pick a value from -1 to infinity. I'm sorry, that's not -1, that's +1. You could pick 2. So when you do 2, store that in the x. Second enter, and hit enter on that, and you get 10, which is positive. Which means this interval is positive. Okay, so, the fact that it oscillates like this, that's just a coincidence. But we want to make our solution set. So our solution set answers the original problem, right? The original polynomial was greater than 0. So that means my original polynomial is positive, right? So I want to find the intervals that are positive. All right, so here they are. Here's the 2 right here on my fingers. So from -3 to 0 and from 1 to infinity. So my solution set is the interval -3 to 0 union 1 to infinity, because they're the ones that are positive. And the original inequality was greater than 0, which means positive. Now, am I going to include these values? Well, I'm not going to include infinity, obviously, but am I going to include -3, 0, or 1? Well, I'm not, because my inequality is strictly greater than 0. It's not greater than or equal to 0. So, if you take -3 and plug it in here, you're going to get 0, right? Because it's a breakpoint. The same is true for 0 and 1. But 0 is not greater than 0. 0 is equal to 0. So I'm not going to include those values in my solution set. So that's how you would solve a polynomial inequality. The same process applies for any polynomial. Factor it, set the factor is equal to 0, construct your number line, put the breakpoints on the number line, do a test value for all the intervals, and then pick the intervals that are answering the original polynomial, whether it's positive or negative. Now, that is for polynomial inequalities. Now, for a rational inequality, 95% of it is the same, but there's one exception. So note, everything about polynomial inequalities pertains to rational inequalities as well. However, with one additional step. So there's one additional step you have to consider. And that is, since we have a rational inequality, since a rational can lead to what? Division by 0, we need to check for the values of x which can make the rational undefined. So, in addition to finding where this is going to be equal to 0, the numerator, so basically with a rational function, or with a rational inequality, this is what we're saying. We have two places where breakpoints occur. Breakpoints occur at 2 spots. Whereas with the polynomial inequality, breakpoints occur when it's equal to 0. With a rational inequality, the breakpoints occur when the rational is equal to 0, which is the same as a polynomial. But here's the additional part, where the rational is undefined. So we have 2 places where breakpoints occur. Okay? Now, I guess I underestimated how much room I needed. Well, if I have to remove that, I will. But I have another example. I just filled it in the notes at the last second, but I should have put it on the other side. But it's okay. So what I have to do is, this is the thing that you should be aware of with rational inequalities right here. We do the first one with a polynomial as well. Make sure the right-hand side is 0. Okay. But with a rational, we have to make sure where the rational is undefined. That's where we have division by 0. All right. Stuff over 0. All right. So, all right. First thing we got to do is what? Make sure the right-hand side is 0. Okay. Now, and I also said this on page 1, is that when you're dealing with a rational inequality, there is only one rational term. You want to make sure there's only one rational term. So basically what you got to do is you got to combine all the rationals you see into one fraction. So first thing we got to do is make sure the right-hand side is 0. So I'm going to subtract the 2. And when I do that, I get 2x squared plus 5x plus 6 over x plus 1 squared minus 2 is greater than or equal to 0. Okay. Now, that's fine. Okay, we're fine there. But I have 2 terms now. I have a fraction minus 2. That's a problem. You have to make, remember, you have to make one fraction. You have to make one fraction for a rational inequality. That's not function, that's fraction. I really miss writing on a board with markers. So how do you do that? Well, you multiply the 2 by x plus 1 squared over x plus 1 squared. Right? You multiply it by the least common denominator of the first fraction. So you're going to get 2x squared plus 5x plus 6 over x plus 1 squared minus 2, right? Now you're going to multiply the 2 by what? You're going to multiply to combine these two numbers, or these two terms into one term. You're going to multiply the 2 by x plus 1 quantity squared over x plus 1 quantity squared. And that's still greater than or equal to 0. All right. You had to do that because now they have the same denominator, so now you can write this as the following. You can write this now as 2x squared plus 5x plus 6 minus 2 times the quantity x plus 1 squared all over x plus 1 quantity squared, which is greater than or equal to 0. So now I have one fraction, right? 2 became 1. Okay, well now, since I combine these two fractions into one fraction, I got to combine like terms. I got to reduce this fraction as much as I can. Alright, so you're going to have to, you're going to have to FOIL and stuff here, right? So minus the quantity, right? So I'm going to have 2 times, now x plus 1 times x plus 1 is what? X squared 1x, it's 2x, and 1 times 1 is 1. So that's the, when you FOIL that out, you get x squared plus 2x plus 1. Now I put a quantity here because this negative applies to everything over here, right? And that's all over x plus 1 quantity squared, which is greater than or equal to 0. Guess I'm getting rid of this, huh? Okay. So now, let's distribute the negative 2, right? So I'm going to have 2x squared plus 5x plus 6, right? So that's going to be, I'm going to distribute the 2 here, so that's going to be 2x squared. But then when I distribute the negative, I'm going to have negative 2x squared. When I distribute the 2 to the 2x, I'm going to get 4x, right? And then when I distribute the negative to that, I'm going to get negative 4x. 2 times 1 is 1, times that negative is negative. I'm sorry, 2 times 1 is 2, times negative is negative 2. And that's all over x plus 1 quantity squared, which is greater than or equal to 0. Okay, ignore this one for now. Alright, so now I could combine like terms in the numerator. Alright, so I have 2x squared minus 2x squared. Well, that's nice. They cancel out. Okay. I have 5x minus 4x. That gives me x. I have 6 minus 2, which is 4. So the numerator reduces to x plus 4, which is sweet. And that's all over x plus 1 quantity squared, which is greater than or equal to 0. Okay, so this is what we have now. This is what we have now. And this is good. This is a rational inequality. In which the right-hand side is 0. And I have, it's completely factored. And I have one fraction. In other words, I have one rational term. All right? I couldn't, so now I'm ready to find my breakpoints. You know what? I'm just going to have to do that example on the other side. So just ignore him for the time being. So I'm ready to make my breakpoints. All right. So let me bring this over here. So my first breakpoint. I'm ready to find my breakpoint. So the first breakpoint is when this equals 0. So when does this equal 0? That's when the numerator equals 0. All right, so how do you solve this equation is what I'm saying. How do you solve that equation? Cross multiply. So when you cross multiply, because this is over 1, right? X plus 4 times 1 is x plus 4 equals 0 times that is 0. Subtract 4, you get x equals negative 4. That's one breakpoint. Okay. That's the only time when this function is going to be equal to 0. Now the next breakpoint. Remember, since this is a rational, I also have to check where the rational is undefined. When, well, I meant to write is, and I wrote it. When is it undefined? This is undefined when I have division by 0. So that's when the denominator, which is x plus 1 quantity squared, equals 0. So just solve that. That's when the denominator equals 0. So if you solve that, take the square root of both sides. X plus 1 equals the square root of 0 is 0. Subtract 1. You're going to get x equals negative 1. That's another breakpoint. So those are the two values that go on my number line. That's it. Where does it equal 0? When the numerator is 0. When is it undefined? When the denominator is equal to 0. Okay, and those are the two places where breakpoints can occur. All right, this is for breakpoints. That's where the function could potentially change from positive to negative or vice versa. So now let's make our number line. We're ready to find our solution set. So, okay, put the break values on there in order, of course. So negative 4, negative 1. So I have 3 intervals to check. 1, 2, 3. All right. So calculator time. So what I'm going to do is, now you're going to check this inequality, right? You're checking this inequality. You're going to type the values into this inequality because that's, you're not trying to make sure it's greater than 2. You're trying to make sure it's positive or negative. All right. All right, so let me type in my inequality here, the left side of it. So that's x plus 4 divided by x plus 1 squared. Ignore that number. Let me pick a value that's less than negative 4. Negative 5. All right, negative 5. Store that into x. Second enter. Second enter. When I type that in, right, that is my inequality, right? X plus 4 over x plus 1 squared. Yeah, okay. It gives me negative 0.0625. So that's negative. Okay. That's negative. Pick a value between negative 4 and negative 1. Negative 2 works. Second enter, second enter. That gives me 2, which is positive. Pick a value greater than negative 1. Well, that's easy. 0. When you put 0 in here, what do you get? You're going to get 4 over 1 squared, which is 4. And that's positive. You could check. You could do that. That's easy. That should give you 4. Oh, wait a minute. Oh, wait. I'm sorry. I did the wrong thing. 0. Second enter. Second enter. That should give you 4. Yep. So that's positive. So you can see how this interval and the middle interval are the same value. Remember, it doesn't alternate like that. You have to check every one. All right, so now I'm ready to make my solution set. So the original inequality, well, not the original inequality, this inequality right here, the boxed inequality. Remember, you're checking the one that has a 0 on the right-hand side. That's the one you're checking. So when you type that in here, or I'm sorry, this is positive, right? This is positive. When the left-hand side is positive and equal to 0. So I'm looking for the intervals that are positive. All right, so from -4 to 1 and from -1 to infinity. Okay, but my inequality here is where it's greater than or equal to 0. Okay, so the breakpoints could possibly be a part of the solution set or not. So I'm not going to just write from -4 to infinity. I'm not going to do that. I'm going to break it up at the breakpoints. So -4, -1, that's the positive, and, or I should say, or -1 to infinity. Now infinity is always open. We know that. Now let's figure out if -4 and -1 are part of the solution set. Well, let's look at -4. So when I plug in -4 in here, what do I get? Well, I did that over here. When does it equal 0? At -4. Right? I determined that right here. This breakpoint makes this 0. So that will be part of the solution set because -4 will give me 0 is greater than or equal to 0, and that is true. 0 is equal to 0. So -4 is part of the solution set. Now what about -1? -1 makes this what? Well, it makes it undefined. If I put -1 in here, I'm going to get division by 0. That can't happen. So -1 is not part of a solution set. And that right there is the solution set to this inequality. Which, you know, when you do this algebra here, you know, when you could bring the two over and combine like terms, it's still the same inequality. And that's it. I'm going to do this problem on the next page because I'm silly. So 3x minus 5 over x plus 2. Is less than or equal to 2. Okay, so what am I going to do here first? Make the right-hand side 0. 3x minus 5 over x plus 2 minus 2 is less than or equal to 0. Combine these two terms into one term. So 3x minus 5 over x plus 2 minus 2. Now I'm going to multiply that by x plus 2 over x plus 2. And that is going to be less than or equal to 0. Now I could write this as one fraction. I could write this as 3x minus 5 minus the quantity, right? It's going to be the quantity of 2 times x plus 2. All over x plus 2, which is less than or equal to 0. Now let's combine like terms in the numerator. So 3x minus 5, 2 times x is 2x, with the negative is negative 2x. 2 times 2 is 4, with the negative is minus 4. All over the denominator, which is less than or equal to 0. Combine the like terms in the numerator. 3x minus 2x is x. Negative 5 minus 4 is negative 9. Over x plus 2, which is less than or equal to 0. So that's what I got now. This is beautiful. I have one rational term. It's completely factored. And the right-hand side is 0. So let's find our breakpoints. So the first breakpoint, when is it equal to 0? So x minus 9 over x plus 2 is equal to 0. Cross multiply. X minus 9 equals 0, which means x equals 9. That's a breakpoint. The next breakpoint, when is it undefined? That is when the denominator is equal to 0, which means x plus 2 equals 0, which means x equals negative 2. That's the other breakpoint. So since those are the only two breakpoints, let's make our number line. So negative 2 and 9. So I have three intervals, 1, 2, 3. All right, we're checking this one. And now we're checking to see where this interval is negative and equal to 0. All right, so pick a test value. Pick something less than negative 2. Negative 3. Store that into x. Let me type in this inequality. So parenthesis x minus 9 divided by parenthesis x plus 2. And that gives me 12. All right, so 12 is positive. Which means I have that. Pick a value between negative 2 and 9. 0. Whenever you could use 0, always use 0. And that gives me negative 4.5, right? It's negative. Which means this is negative. All right? Pick a value that is 9, right? Pick a value greater than 9, so pick 10. 10. And that gives me 0.083, so that's positive. Which means this is positive. Okay, so now that I filled out my number line, I'm ready to create my solution set. So which intervals answer the original inequality? When it's less than or equal to 0. So when it's negative. That's the middle interval. Negative 2 and 9. Now I want to see if negative 2 or 9 are part of the solution set. So is negative 2 part of the solution, yes or no? It's not, because negative 2 makes it undefined. So negative 2 will not be part of the interval. Will not be part of the solution set. Will 9 be part of the solution set? Well, 9 makes it 0, and since it's less than or equal to 0, it will be part. So that right there is my solution set. And that's it, ladies and gentlemen. That's it. So when you're solving polynomial inequalities or rational inequalities, they're 95% similar. The only difference between them is with a rational inequality, you have to check this additional step. When is the rational undefined? And you have to have one rational term. One rational term. So if your right-hand side is not 0, make it 0. But then you're going to have to combine the terms together to get one fraction. Regardless if it's a number or another polynomial over here, you have to get one fraction, right-hand side 0, every time. If you remember that, you'll be fine. You'll be perfectly fine. And you don't have to remember it if you just get enough practice. So that's it for this section, and that is it for Chapter 5. That's the conclusion of this video.